Okay, I promised you a review on related rates, and so here it is. And it's actually a little more than a review. It's actually I'm going to be covering that section again. Uh, so, as you may recall, related rates just means that the rate at which one thing is changing with respect to another is related to another rate of change. And the example I gave is that the rate at which the price of gasoline rises or falls is related to the rate at which OPEC raises or lowers their price per barrel of oil. Now, in these questions, there will be one or more rates that are given as numerical values, and one or more that can be calculated, and then one we will be solving for, and that will be the answer that we're seeking. Now, I'm going to start with a question that we did not, that I did not cover in class, because there is a question on your exam a lot like this first one I'm going to be covering. It's an abstract example, meaning that there's no word problem to interpret, but you do have to understand that there's a third variable that isn't visible in the equation that you're given. So, there we go. Hello? Okay. All right, so yes, I said it's abstract, and the values that we're working with in this particular example are presented in a slightly different way than they were with our applications, in other words, our word problems in class. But we still have one rate that is given as a numerical value and one that we'll solve for. What's different is how we calculate, and you'll see that in the next couple of slides. And as I said, I haven't gone over a question like this yet, so that's why I'm doing this now. Alright, so here's our problem. Here's our question. We have x squared plus y squared equals 4, and we are told that dy dt, the rate at which y is changing with respect to t time, when x is equal to 1.2 and when y is equal to negative 1.6, that rate is 5. And we're asked, what is dx dt, the rate at which x is changing with respect to time? Now, example 3 on page 592 of our text is almost exactly like this question. The only difference is that we're asked to calculate dx dt here, or determine dx dt here. And that example in the book is the same, it's just that you're looking for dy dt. That is an inconsequential difference. It's just, the difference in a letter. So, excuse me, having some coffee. So x squared plus y squared is equal to 4. This, by the way, is the equation of a circle with a radius of 2. Square root of 4 being 2. And so we need to differentiate this, but because we are looking for dx dt, we see x squared as a function of t. We also see y as a function of t. So that means that we have to differentiate both of these using the chain rule, and in fact, not just the chain rule, but implicit differentiation. And instead of just differentiating this y term and tacking a y prime on the end, we're also going to do the same thing for the x. We're going to differentiate the x term and tack an x prime on the end of that. So the derivative is 2x, but then we tack the x prime onto it, and here the derivative is 2y, but we tack that y prime onto it. Now that x prime and that y prime, since these are functions of t, those are dx dt and dy dt. So 2 times x times dx dt plus 2 times y times dy dt is the new equation. That's the new way of writing the equation. So we're writing this prime as dx dt and this prime as dy dt. And we are given that x is 1.2 and y is negative 1.6. So we substitute those in and multiply the 2 times 1.2, that gives us 2.4. Multiply 2 times negative 1.6, that gives us negative 3.2. But we were given in the question that dy dt is 5 when this x and y are that value. So that's given that dy dt is 5. We now have only one unknown and a bunch of numbers. So we just multiply the negative 3.2 times 5, and that gives us negative 16. And then we add 16 to both sides, so we have 2.4 times dx dt is equal to 16. And then we divide the 16, we divide both sides by 2.4 to clear the 2.4 over here, and that gives us dx dt is equal to 16 over 2.4, which reduces to 2/3. So that is the answer. dx dt is 2/3. Now, the next question is one that I went over in class. It's an application, but before I go there, we will have, so that's how the last example is how you would answer one of the related rates changes on the second exam. The next one is how you would answer the other, which is an application. And excuse me again, having some very delicious coffee this afternoon. And so there's going to be one rate that will be given as a numerical value and one rate that will be calculated and one we solve for, and we'll have an equation that looks something like this. dy dt is equal to dy dx times dx dt. The dx's cancel just like variables or units or numbers. And in this question on your exam, this first value, the value on the left, that is the value that you're actually seeking, and so one of these will be calculated and one will be given. Another way of looking at this is to see that we're given in the question coming up two numbers and one function. One number is going to be a rate. That won't require any calculation, and that rate will be this rate in this position in the equation, or it will be in this position in the equation. So one number will be a rate, and then we will differentiate the function that we're given, and the second number then gets substituted into that derivative to calculate the other rate. So we'll have two numbers, we'll multiply together, and that will give us our answer, the rate we're seeking. And this table here is, I reworded it. I took out a step, and I reworded it from the table that's on page 591. Both my version and their version are helpful. I think it is often helpful to see the same thing worded slightly differently from two different perspectives. Okay, now we probably remember that there was a pond that was still like glass, and we dropped or threw a rock into the pond, and as you can well imagine, there is a circular ripple that starts expanding. It starts, the ripples are, and the outer circle is moving out, and so the radius of the ripple is increasing, and of course, obviously, we don't need calculus to know that. We know just from our experience, and we're told that the rate that it's increasing is 2 feet per second. And the reason we know it's a rate is this increasing and per second. So this is a d something dt. D what dt? It's dr dt, the rate at which the radius is changing with respect to time. We are given that number, that is 2. This is the rate that we are given in this question. Okay, and so now we have 2 numbers in one function given. So the number that I just talked about is 2, and that is dr dt, the rate at which the radius is changing with respect to time. So now we've got that portion of the equation. 2 is equal to dr dt, and we have a function. And we know that we need to differentiate the function. Well, this is our, so to speak, f, and this is our, so to speak, x. So we want f prime of x, except in this case, it's a and r. So we differentiate a and r. Well, pi is just a number. This may as well be 7r squared, except it isn't 7, it's pi. Pi is just a number. It's a Greek letter, but in mathematics, it's just a number. So we differentiate this function, and so we use the power rule, bring the 2 around front, 2r, subtract 1 from the 2, and so this is 2r to the first, 2r to the first, and so that derivative then is 2 pi r. And I just pushed the 2 to the front of the line here because when we multiply, we can put anything in any order that we want. So that then is a prime. A prime equals 2 pi r. Well, we know what the r is. The radius is given. That other number is the r. It's the r in this derivative. So the derivative evaluated at 10 is 2 pi r. R is 10, so that's 2 times pi times 10, which is 20. And in Leibniz notation, that's the d something up top, d something in the bottom, the denominator. That's going to be dA dr. dA dr. A prime is the rate at which area is changing with respect to radius. Okay, so now we have the dA dr and the dr dt, but we're being asked for the rate at which the area is changing with respect to time. So we substitute the known values, one we were given and one we calculated, into the equation dA dt is equal to dA dr times dr dt. The dr's cancel, and that gives us the dA dt. So 20 pi is the dA dr, and we were given dr dt is 2, so that's 20 times pi times 2, and again, like I said, we put the 2 out front, and so that's 2 times 20 is 40, so this is 40 pi feet per second. That's the final answer. Now, when you are working these questions out, it's very important, or at least it's extremely helpful, to be able to look at these and realize that the numerator, so this is the rate that whatever this value is in the numerator is changing with respect to this thing down here. The volume of a hot air balloon is increasing. That volume is increasing with respect to the altitude that the balloon reaches, and various things like that. So when you're looking at these application problems, it's very important to be able to translate what's in the question into these Leibniz notated derivatives. Okay, now our last example here is a business application, and so I think this might be straight from the text. I can't remember actually, but we have a company that has calculated their costs and their revenue for the manufacture and sale of sports supplements with these two functions. And X is the quantity of bottles they make, and the cost at 743, 120, however many bottles, the cost at this level of production, whatever it is 125,000 plus 0.75 times however many units that is. That's the cost function, and the revenue is 250x minus 1/10 x squared. Now we are given that the current level of production is 1,000 units, and it's increasing at the rate of 150 units per week. We're asked what rates cost, revenue, and profit are changing with respect to time. With respect to time means dt in the denominator. So we want the rate at which cost is changing with respect to time, and the rate at which revenue is changing with respect to time, and then we can use those two to calculate the rate at which profit is changing with respect to time. And now at this point I'm going to switch over to the handout that we used in class. And so dc dt, the rate at which cost is changing with respect to time, is the rate at which cost is changing with respect to quantity, times the rate at which quantity is changing with respect to time. Your question on the exam will be exactly like this, except there will be different numbers, but everything else will be exactly the same as this. So that's how we determine dc dt, the rate at which cost is changing with respect to time, and here's how we determine the rate at which revenue is changing with respect to time. We multiply dr dx times dx dt. This is the rate at which revenue is changing with respect to quantity times the rate at which quantity is changing with respect to time. So we differentiate the 125,000x, or we differentiate the 125,000 plus 0.75x. Well, that's just a linear function, and so c prime, or dc dx, is 0.75. Now we were given the rate at which quantity was changing with respect to time as 150. And so that's a very easy substitution. You have the 0.75 for your dc dx, and dx dt, the rate at which quantity is changing with respect to time, is 150. You substitute that in, you multiply, and 0.75 times 150 is 112.5. Now, that's our dc dt, the rate at which cost is changing with respect to time. Now for the revenue, that's another easy derivative. This is a linear term, so we just bring along the coefficient, and we bring the 2 to differentiate this term. We bring the 2 out front. 2 over 10 is the same as 1/5. Subtract 1 from the 2, and so this is 2 over 10 is 1/5. So this is 250 minus 1/5 x. X is a particular quantity. What quantity? Well, that quantity was given as 1,000. That quantity was given as 1,000, and the dx dt again is the same as the dx dt here. It's 150. And so we substitute those into the second equation to determine dr dt, the rate at which revenue is changing with respect to time. So 250 is just a constant, and x is 1,000, so we substitute 1,000 in here, and 250 minus 1/5 times 1,000 times 150 is 7,500. So that's dr dt, and we already have dc dt, and so the rate at which profit is changing is just the difference between the rate of change of revenue and the rate of change of cost. So 7,500 minus 112.5, so that's $7,387.50 per week is the rate at which profit is changing. Okay, so there we have it. If you have any questions, you can text me, you can message me in Canvas. If you use the Canvas communication, that somehow works out better, I'm told, but you can email me and it'll get to me just the same. Okay, see you Thursday.